Hi, I'm Sidharth, and this is my video for teaching a topic in 13.5, chain rule with one independent variable. Okay, so I'm going to go and start off by explaining a simple concepts in single variable calculus before jumping into multivar. You might be familiar with a function y in terms of x. For example, y is equal to x to the power of 3. Over here on the right, we have a graphical interpretation of this function. You can see as x increases, y increases, right? Because it's an odd function. Now, if we want to predict the value of y, some delta x from like an initial point over here, we can use the concept of a slope or a line, right? So we can find the slope at some point, like right here, and we can multiply the slope dy over dx by a change in x, delta x, to predict dy. And this dy is an approximation of delta y. And as delta x becomes infinitesimally small, then our approximation becomes more and more correct, and the dy approaches delta y. Similarly, we can have a similar expression with a different variable. For example, instead of y being in terms of x, we can have y being in terms of t, and the same expression holds true. Or we could also have x being in terms of t. So this is all good and dandy for single variable calculus, which is a prerequisite for this class. But there's also multivariable functions. For example, z is equal to f of x and y, where z takes both inputs x and y. And also, we can add another layer of complexity, specifically because we're going to talk about the chain rule, where x is a function of t. So we have z is a function of x and y, and x is a function of t, and y is a function of t. Now, as dt goes to 0, dy and approaches delta y, and dx approaches delta x. This is important for like a multivariable function graph over here, right? What this graph is showing us is in the yellow is the function of f of x comma y, right? Where if you have x, y pair, coordinate pair, the function will map it to an output z. If we want to predict an output, our predictions get better and better using this parallelogram. So if we know like a point over here, and here let me use a different color. If we know like a point over here, and we want to get close to this point over here, we can add a certain delta x over here to the x and to the x coordinate, and a certain delta y over here. And then together, those will get us to x plus delta x and y plus delta y, because we have two variables. And since we want to figure out what delta z is, not dz, as the delta x becomes really, really small, our dz will approach delta z. You can see over here that if we just look at the xz trace, there's kind of a secant line where z is in terms of x, and then we can like go back to our graph over here. So as delta x gets really, really small, dz approaches delta y. And then instead of it just being dz is equal to just something in terms of x, dz is equal to the partial z over partial y times delta y plus partial z over partial x times delta x. So these two sums give us this sum of the two terms gives us the total change in z, and this gets closer and closer to the actual change in z as it gets infinitesimally small, as delta x and delta y get infinitesimally small. So that's what leads us to this expression over here. And this expression is really the key to understanding the multivariable chain rule, because we already know that dx is equal to dx over dt times dt, and dy is equal to dy over dt times dt. So if we plug in those values, knowing that as dt goes to 0, dy approaches delta y and dx approaches delta x, we can just plug in the value for delta x with the value for dx over here, and then we have this expression over here, and we can do the same thing for delta y. So delta y essentially equals dy, and then dy is dy over dt times dt. So then we get this over here. Now, finally, to get our multivariable chain rule with one independent variable expression, we can just divide both sides of the equation by dt. So over here we have a over here we have a dt, and we just want to divide both sides of the expression by dt. So then that way we get dz over dt is equal to partial z over partial x times times dx over dt plus partial z over partial y times dy over dt. And this makes sense if we just look at it, because the partial x kind of cancels out with the dx. So then we're kind of left with like the change in z with respect to t for x, and the change in z with respect to t for y. And if you add those sums together, it kind of makes sense that that's the change in z with respect to t as a whole, as shown over here, right? Where this is like just the change in z, this is the rate of the change in z. So that's where we get our chain rule with one independent variable. Now, let's say we want to apply this knowledge to the real world, right? For example, in chemistry, there are actually many situations in which the rate law has the change in concentration of A and B, where you multiply those two things together. And we can just say that A is represented by x of t, and then the concentration of B is represented by y of t. So they're changing differently with respect to time, and also the concentration of A changes differently than the concentration of B. This is especially common in the case of asymmetric reductions and other reactions involving different ketones and different organometallic catalysts. Like I specifically saw this in research that I did at a university chemistry lab. But anyways, there's many situations in which you will have a function that changes in more than one variable, like x and y, and also changes in terms of t. This is just one example of a problem like that. Also, one small note is that in this textbook theorem, it says that we have w in terms of x and y, whereas above I just use z. Of course, you can use any variable you want. So for this specific problem, how do we use the multivariable chain rule, right? So first, we need to differentiate z in terms of partial x. We can just take the partial derivative of z with respect to x. And then over here, we need to be careful that since we're doing a partial derivative, we do not care too much about y, and we treat it as a constant. So that just goes over here. And then for x, the terms with x, e to the power log base 2x. Log base 2 is essentially ln x over ln 2. So then the derivative of that is 1 over x times 1 over ln 2. So then we use the regular chain rule and multiply those at the bottom. So over here is the derivative of this. So this whole thing is the derivative of the x term, because we have a function inside another function, so we have to use the chain rule. Similarly for y, we don't care about x anymore, right? We just care about y. So when you do the partial derivative of y for z, partial z over partial y, then we know that the derivative of arccosine of y is -1 over y squared plus 1, and then we just multiply that by the x term. So over here, this is the x term, just multiply by the x term, and then yeah. And then finally, dx over dt is just going to be ln2, because that's a constant. So yeah. And then dy over dt is -1, because yeah, that's just how you apply the power rule. And then over here, we're gonna finally apply the multivariable chain rule. So I'm gonna use a different color. So we're gonna multiply partial z over partial x by dx over dt to get the rate of change of z with respect to t for x in some ways. So the ln2 is going to cancel out with the ln2 at the bottom. So then we're just going to be left with the e to the log base 2 of x times arccosine y divided by x. Similarly, for the y side of things, we're going to multiply partial z over partial y by dy over dt, I misspoke. And then we're going to just, basically the negative sign cancels out, so it just becomes positive e to the log base 2 of x divided by y squared plus 1. And then we can simplify further, because we want our expression to be in terms of just we want an expression like with the rate just to be in terms of t, because we want to see how much z changes in t, not how much z changes with x and y. So we have a bunch of x's and we have a bunch of y's, so we want to replace those with the t's. So x is equal to ln2 of t, so we just replace that. Y is equal to -t, so we just replaced it over here. X is equal to ln2 of t, so we should replace that over here. X is equal to ln2 t, so we replace that over here. And then finally, since y is equal to -t and it becomes y squared, so and it's y squared plus 1, then it becomes t squared plus 1. Okay. I hope that explains the multivariable chain rule with one independent variable. Thank you for listening to my video.